Last example was a bit brief. Let's go into more depth by looking at competing species. This is a ecological model in which we're taking two species, X and Y, and we expect them to behave according to a logistic equation. But on top of that, they're competing for the same resources. So we add a term that is alpha times the other species. So for dx dt, we add the term minus alpha 1 y, and for dy dt, we add the term minus alpha 2x. That is the interference given by the competition of each species. If one of the two species is eating a lot of food, then the other species is not able to find food. So we have a lot of parameters. We have epsilon 1, sigma 1, epsilon 2, sigma 2 given by the two logistics equations, and we have alpha 1 and alpha 2. The 6 parameters are all positive and real. So we try to study the qualitative behavior. So the first step is we look at an example in which we chose some values for all the epsilons, sigmas, and a's, and we have dx dt is equal to x times 1 minus x minus y, dy dt is equal to y divided by 4 times 3 minus 4y minus 2x. To study the qualitative behavior, so an understanding of what is happening in the situation, the first step is computing the null clients. So we want x prime equal to 0. That gives us either x equal to 0 or x plus y equals to 1. And we want y prime equal to 0. That gives us y equals to 0 and 2x plus 4y equals to 3. We can rewrite this as y equals 3 minus 2x divided by 4. So now we have 4 null clients, 2 for x prime and 2 plus for y prime, and we can draw them. In red, I have drawn y prime equal to 0, and green, I have drawn x prime equal to 0. That means on the green row lines, the curves possibly, we can only move vertically. On the red lines, we can only move horizontally. Now I'm going to zoom in on the positive quotient, and we're going to look at this. We can find the critical points as the intersections of the green lines and the red lines. You need one green line and one red line to find the critical point. If a green line intersects itself, that means that, well, x prime is twice equal to 0. That gives us no information about equilibrium. So as before, we remember that on the x prime equal to 0 lines, that is the green lines, the null lines, we can only move vertically. On the red lines, y prime is equal to 0, we can only move horizontally. Then we compute the sides of x prime. We only have 2 areas to consider because we are only considered the positive quotient. And in these 2 areas, we can just compute any point in there gives us information about x prime. So the infinitely long blue area has x prime negative. The other little triangle has x prime positive. That gives us information about the fact that this little green triangle, we're moving to the right. The infinitely big blue area, we're moving to the left. We do the same thing for y prime. We divide our positive quotient into a blue area and a green area bounded by the null lines we just computed, and we check the sign of y prime in there. So we find that the infinitely long blue area has y prime negative and the little triangle has y prime positive. So in the blue area, we're moving downwards. In the green area, we're moving upwards. So we merge the information we found for x prime on its sign and the information on the sign of y prime. So we have a big area in which x prime and y prime are both negative, a little corner in which they're both positive, and then the connection between the two has one positive and one negative, and we have to be careful in which is which. Now that we have divided our phase plane on areas in which we know the sign of each of our derivatives, we can fill it with arrows. Something like this. We can start having some understanding about the behavior. For example, we have a vertical line in which x prime is equal to 0. That means that nothing can cross it. If you're on the right of it, you stay at the right of it. If you're on the left of it, you stay at the left of it, because at the line, you're not moving neither left nor right. The same you can say about the horizontal axis in which y prime is equal to 0. If you're at the right of it, you stay at the right of it, because you can never cross this. We can also notice that in this like two little triangles on the side, everything is coming in. We are bounded by one side that we cannot cross, and on the other two sides we're getting inside in both directions. That means we have all the trajectories are coming in, and they have to be coming out in some ways. So we already have some vague understanding about how this all behaves. Let's try to study the linear behavior at the critical points. So we compute the Jacobian, df with respect to x and y, dg with respect to x and y, and we have this matrix depending on x and y. So it's 1 minus 2x minus y, minus x minus 1/2 y, 3/4 minus 2y minus 1/2 x. And what we want to do is compute the Jacobian of all the equilibria and figuring out the linear approximation. And this is exactly what we're going to be doing. At 0, 0, we have the Jacobian being 1, 0, 0, 3/4. So the eigenvalues are 1 and 3/4. It's an unstable node. This is a linearization that is reasonable because a perturbation of it will still give us an unstable node. The same we can do at 1, 0. Then the Jacobian becomes -1, -1, 0, 1/4. That gives us the eigenpairs -1, 1, 0, and 1/4, 4, -5. This is a saddle node. Again, this is a linearization that we can handle. That means that if we go back to our plot, we have that at 0, 0, we have an unstable node. And at 1, 0, we have a saddle node. That is, on the horizontal axis, everything is moving towards it. And at a slanted direction, things are moving away. We do the same for the other 2 points. And we find that at 0, 3/4, we have a saddle point. And at 1/2, 1/2, we have an asymptotically stable node. That means that at 0, 3/4, we again have the behavior in which in two directions things are moving towards the saddle point, and in one direction things are moving away. While at an asymptotically stable node, everything nearby is moving towards the stable node. Let's try to plot that. We have at 0, 3/4, in the vertical direction, things are moving towards the node, and the kind of horizontal direction we're moving away. And at 1/2, 1/2, everything is moving towards it. So now we have some information about what happens at the critical points. We're going to try to connect this information. We use the very important information that trajectories never cross. It's very useful in 2D because we only have one plane in which to move, so we cannot jump the trajectories. And yellow top triangle, the only way out for everything that gets in is towards the asymptotically stable node 1/2, 1/2. The same is true for the other yellow triangle. Things come in through two sides, they need to go out somewhere. So we are expecting the behavior of these two triangles to be squishing and pushing towards a stable node. Then we have the information about the saddle nodes, the unstable node at 0, 0. So we start having this understanding that from 0, 0, you have two lines that go to the other two equilibria, and then one line that connects that equilibria to the stable node. And then we try to understand what else is happening. And we notice that almost everything ends up, after infinitely long time, at the stable node 1/2, 1/2. So we can talk about the basin of attraction, that is everything in our positive plane except the x-axis and the y-axis, because those ones stay on themselves.